In this video, we'll talk about graphs and equations of exponential functions, so follow along in your notes. Here are some pictures of some exponential functions. The two that you'll mostly be working with will be shaped like these two here, where as you read your graph from left to right, you'll find that as the x values are increasing, the y values will do two different things. So in the first graph here in letter A, as we read from left to right, as our x values are increasing, our y values are increasing. So we call this growth. This is an exponential growth graph. But in letter B, as x is increasing, right, as we move from left to right, as the values of x are increasing, the values of y are decreasing. So we call this one exponential decay. So we have growth, anything that increases from left to right, and decay, anything that decreases from left to right. Let's take a look at an exponential function equation. So exponential functions follow the form of a times b raised up to the x power. So anything with an exponent is not an exponential function. So if I had something like, let's say, y equals x to the second. That has an exponent, but it's not exponential. To be exponential, your exponent needs to be x. That's what makes you an exponential function. And just like in the linear functions we studied earlier, the coefficient of x was the rate of change, and the value of b was the initial value. And we can find those two things with an exponential function as well, except they're in different locations here. A, which is the coefficient outside here, is the initial value. So that's the same as the b in the y equals mx plus b functions we used to study. So that is the value we're going to start with. And then this value here, the letter b, which is the base of our exponent x, that is our rate of growth or decay. So you can't call it a rate of change anymore. You have to be really specific. You either have to say it is a rate of growth or it is a rate of decay. You can't just say b is the rate of change. You have to really interpret that value. So let me show you a couple of examples of what I mean. So here are some examples of exponential growth on the left and exponential decay on the right. So take a look at these equations and see if you can formulate an idea of what the difference is between how the equations look. What's something that's different between the growth equations that you see in the decay equations? All right, so have you kind of formulated an opinion here of what you think would quantify something as growth or something as decay? So now I'm going to show you some more examples, and I want to see if you can refine your explanation of what you think is the definition between these two. Here are some other examples. So I want you to think about what you said before, right? Before we were looking at these examples, and most students say, oh, okay, well, decay has this type of rate, whereas growth has these types of numbers as their rate, right? So some people say, oh, growth is a whole number and decay is a fraction, right? So then I showed you some more examples, and hey, what do you know? That's growth, but it's a fraction. And hey, these aren't fractions anymore, they're technically decimals. So let's see if we can really refine our definition here of how we can determine if something is growth or decay. So I guess it doesn't necessarily mean that it has to look like a fraction, right? Because in these examples, they look like decimals. And really, fractions and decimals are the same thing, right? They're rational numbers. But what do we notice about all of these rational numbers, which are generally the same equivalent sort of as these types of fractions we had in our last example? So what do we notice about these decimals that's different than these decimals? So all of our decay values are going to be between the value of 0 and 1, right? They can't be 0 and they can't be 1, but they can be between 0 and 1. So we can have a fractional value, But if it has a value that's higher than 1, then it's growth. And if it has a value between 0 and 1, then it's decay. So that's what defines our exponential growth functions. Any number can be the initial value. But unlike linear functions where your rate was negative and that meant that it was decreasing, we don't have negatives in exponential functions that we're studying. So instead of it being negative, the base value here, right, our rate of change value here will be a fractional value, something between 0 and 1. So in your notes, you have these examples on the left-hand page that show you what some of the examples might look like and ask you to identify their parts. So if I ask you to identify the initial value, you're looking for the number here in the A position. If I ask you to identify whether it's growth or decay, you're looking for that base value of the exponent. So this has an initial value of 2 in our first example. It has a base value of 3, so that represents growth because it's greater than 1. And then the actual rate of growth, right, is a factor of timesing by 3. In our second example here, our initial value is 8. It is a fractional value between 0 and 1, so therefore it's a decay. And then our rate of change is a decay of multiplying by 1/2. So each time our value will go down by 1/2. So we start at 8, then we go down to 4, then we go down to 2, then we go down to 1, right? So we decrease by half each time. And then with our last one here, see, we don't want to be too tricky, but in our last one here, we don't have two values, right? We don't have both of these values here. So the question is, which one is missing? And since this value is the base of the power, that means that this is the B value, right? So even though it doesn't have parentheses, that is the base of the power. So that makes the A number invisible. And the only invisible coefficient we can have is a 1. So that's why our solution here says the initial value is 1. And its base is higher than 1, so therefore it's growth, and its rate of growth is a factor of timesing by 5. So why don't you take a look in your notes now and see if you can complete these 3 questions. Pause the video, write your answers, and then come back to check your solutions. All right, so first we ask you to state whether it's growth or decay. So this one is growth because the base value is higher than 1. Then we ask you to state the initial value, right? That's the A position number here. So the initial value, or the y-intercept, is 4. And then it asks you to identify the common factor, or the rate of change, and that would be the rate of change is a growth of timesing by 3. For number 2, we have decay, because it is a fractional value. We have a y-intercept, or initial value, of 5. And we have a common factor of 1/3. And in the last one, remember that x is a little low, but that x should be an exponent like this up here. And our function here is growth. And our initial value is an invisible 1, and our common factor here would be a multiple of 2. All right, so the next few things we're going to talk about are the vocabulary words domain and range, and maybe their end behaviors, or whether they have some type of boundary or asymptote. So let's take a look here. This exponential function is a growth function, right? So it's increasing as we move from left to right. So the domain, which are all of our x values, the domain is how far left the graph goes. Well, it looks like it goes all the way to negative infinity. And then to the right, it goes all the way to positive infinity here. Right, so positive infinity, negative infinity. And so when we write our domain, sometimes we write it as an inequality like this. So it stretches from negative infinity all the way left to positive infinity all the way right. We could write it like this. We could write it in interval notation, such as this, with a comma that separates them. Or we can just state that it's all real numbers, right? All real numbers. And if we're feeling really fancy, we can use this double bar R instead of that English sentence, right? All real numbers. So that's the domain, right? That's the domain values here. Now if we look at the range, which is how high up and how low down the graph stretches, it looks as though we go up to infinity, but we don't go down to negative infinity. It looks as though we don't cross this x-axis here. So that means that all of my values go from 0 up to infinity, right? So we could write our range like this as an inequality. We could write it in interval notation. But this is the most common way to write the range, and that is if you're just all the positive numbers from 0 on up, you just say you're any number greater than 0. And this is where it kind of gets a little tricky. Let's look over here at this graph to the right. Let's say we had an initial value of 1, and let's say our decay factor, right? This is a decay factor here. So let's say it was 1/2. So if this was our function, then our initial value would be 1, but then as we move down the graph, we would reduce by half. So this would be 0.5, and then this one would be 0.25, right? And so on and so on. And it looks as though it approaches this axis here, but it never actually crosses it. See, it never actually crosses it. It just kind of grazes it. Because each time as I reduce, if first I was 1, and then I'm 1/2, and then I'm 1/4, and then I'm 1/8, and then I'm 1/16, and then I'm 1/32, I never actually will be 0. I just keep being half of what I used to be. So I approach this line, but I never actually cross it. Never actually cross it. But we get closer and closer and closer, and we get so close that our eyeballs can't even really differentiate how much closer we're getting with each iteration here. And this is kind of like what we call a boundary, right? Where it's like a fence. It gets really close, but it never actually touches it. And we call that an asymptote, right? This P here is silent. An asymptote is that imaginary line here that the graph is approaching but never actually crosses. So for us, in these two examples, it conveniently is the same line every time. So for this example, the asymptote of the boundary here is the line x equals 0 here, right? Y equals 0. It's a horizontal line. X equals 0 would look like this. And this one is the same. That's the horizontal line of y equals 0. So those would be our asymptotes. Those would be our asymptotes at the end. So why don't we take a look at our graphing calculator and just kind of see if we can enter a function in and see if it gets this nice kind of what we call J-shaped curve, right? So let's turn our calculators on, and let's go to our y equals button, and why don't you try entering this function here, y equals 5 to the x. So press your y equals button, and press y equals 5 to the x, and that's how you're going to enter your equation into your graphing calculator. And then you can look at the graph, right, by pressing the graph button. Now this isn't going to get it on your paper, but it can certainly at least show you the shape of the graph, and you can look for that J-shaped curve. Is that what we're looking for? Yes, that's what we're looking for. So if we actually wanted to draw it on our paper, we'd have to copy down a couple of these actual points, which they're hard to see with our pixels here. So why don't we look at our table? Why don't we look at our table by pressing second table, and there we can see some of our points, right? There we can see some of our points over here. Now there's a lot of points because it gets really high really fast, right? It's going by 5s every time. So let's see here. If I were to press the up arrow, right, and go into my negatives, I would see this screen over here. Right, I would get 1, 0.2, 0.04, 0.008, and the number's going to get so small that the calculator uses scientific notation just to show it to you. That's what that E means. 3.2 e to the negative 4th means I am actually 1, 2, 3, 4 places smaller. This is the actual number. This is the actual number, but it's so small we're not going to graph something like that. All right, so let's take a look at our calculator's table again, and let's see if we can find our y-intercept. Right, our y-intercept is always that value where x is 0, so our y-intercept is 1. And then when we're looking at the graph, right, we can also kind of identify if there are any limits or asymptotes here, right? Looks like it approaches the x-axis but never actually crosses it. So why don't we practice in our notes here? You should have these examples in your notes. Why don't we practice graphing some of these with our calculator? So we turn our calculators on, right? Let me get my calculator ready here. Turn my calculator on. And let's see. Let's enter this equation. So let me move it over to the right a little bit. And our first equation is y equals 2 to the x. So I press my y equals button. I enter 2, raise it up to the x power. Now I can look at the graph and that's really pretty and nice, but that doesn't get it on my paper. So what I want to do is just keep this drawing in mind that, okay, that's kind of what my end result should look like. But I'm going to press second table and I'm going to write some of these points down on my paper. So I'm going to show the person who's reading my paper what points I'm going to use. I'm going to arrow up a little bit, see if there are some good points here. All right, so these are all going to be like estimated points, but I'm still going to copy them on my paper. So here we go. Let's get a marker. Let's start copying down some of these values. So maybe I'll do like 5 or 6. So I can't graph 16, 32. So I can't graph those, right? But I could graph 8, 4, 2, 1, half, a quarter. I think I'll start with a quarter. So negative 2, 0.25, negative 1, 0.5. And you should be writing this on your notes as well. So it's always important to write down some of the data so that the reader can check to see what you're graphing. 0, 1, 1, 2, 2, 4, and 3, 8. All right, so there we go. So I'm going to start graphing here at 3, 8, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. And then 2 is 1, 2, 3, 4. And then 1 is 2. And this one's 1. And then these are my little decimal values here. So I'm just going to approximate. Like half, 0.25, right? And I'm going to connect these with a nice soft curve and an arrow. And be careful down here. Remember we said we approach the line. But don't be silly and kind of get lazy and draw it like that. You don't want to do that, right? You don't want to make it appear as though it's going below. So we'll just put an arrow right there to say that we know it extends, but it doesn't actually go past that line. And if I look back at my graph, it should look very similar. That's perfect. All right, so let's start taking some notes here. What is our y-intercept? Well, I can either see it from my table or see it from my graph. You can write it as a point, right? 0, 1. My domain is all the way to negative infinity, all the way to positive infinity. So I'm just going to write all reals. Looks like my range is from 0 up to infinity. So I'm going to write greater than 0. And it looks like my asymptote is the actual axis here. And it's always going to be a horizontal line for us. So it always starts with a y and an equal sign. And for us, it happens to be the x-axis, which is y equals 0. All right, why don't you pause the video and do the same thing with question number 5. See if you can give that a try. And I'll get this calculator ready here. For question number 5, our initial value is 3. Our rate of change here is a fraction, so this means we have decay. So this exponential function will be decreasing as we move from left to right. When I take a look at this table here, and I'm going to scroll up until I think about here, because it looks as though my values are getting larger than my graph. So let's see what we've got. We've got a negative 324. Well, that won't fit. So I'll start with negative 212, negative 1, 6, 0, 3, 1, 3 halves. Now, if looking at this as fractions is difficult for you to understand its value, you can always modify your equation here in the y equals button so that instead of this value being a fraction, if I delete that fraction, I can actually insert the decimal equivalent. Since 1/2 is a terminating decimal, I could enter it as 0.5. And when I do that, and I look at my table again, you notice this time my table has decimals. So if you enter it as a fraction, the table will contain fractions. If you enter it as a decimal, the table will contain decimals. And this might be a little bit easier for you to kind of estimate the location point of these fractional values. So 1, 1.5, 2, 0.75, and 3. That's just going to be a little bit difficult for me to guess. So here we go. Negative 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Doesn't fit. So negative 1, 1, 2, 3, 4, 5, 6, 0, 3. Let me take away some of these distracting marks. 0, 3. 1 is 1.5. 2 is 3/4. And then it goes down from there. And you'll notice that it drops off ever so slightly, but it's going to hug that x-axis. It is not going to go below it. So be careful when you're graphing, you don't get lazy and do something like that. Okay, so you do want to hug this x-axis or the asymptote line down here. So our y-intercept can be seen right from our equation, but we can also see it on our graph. It is the point 0, 3. The domain is all reals, and the range looks like it's the same as the last one. It's going to be all of the y values that are greater than 0. And our asymptote is going to match the last one as well. It hugs the x-axis here, and the asymptote is horizontal, so that's a y equals sentence, and since it's the axis, it will be 0. And that concludes our lesson on exponential functions and their graphs.